Hey, everyone. Thanks for coming. Thank you to all the organizers for such a great job. I knew this workshop was going to be in good hands when I heard that with the names of all the organizers. Thank you, Hoa, Suk, Sarah, Chilpa, and Dave. So I didn't know what to prepare really for the opening session. So I thought I would start with Stokes equations. That's always a safe place to start. So I'm going to talk about something that I've been thinking about recently, and we'll see how it goes. It's the first time I talk about it. So we're going to need Stokes equations and the fundamental solution, which is the Stokeslets as we know it. There will be some regularized Stokeslets, and there will be some singular Stokeslets. This is the general expression for a regularized Stokeslets, where there's a let's see, there's a cutoff function phi, and then we can derive some of these, or define some of these functions, the regularized Green's function and biharmonic, and then we can write down an expression for the velocity. This is an exact solution of the Stokes equations for that forcing. And then I think there'll be a lot of details given in the tutorial, so I'm gonna just leave it at that. So here it is, right? In 2D, I'm gonna stick to 2D for a lot of what I'm gonna say. And this is the Stokeset in 2D, and here's a regularized version. All right, so here's what the idea is that I've been thinking about, is that the way we regularize things should really depend maybe on the dimension of the forcing function. So for example, we have scattered points in the fluid in some model, then perhaps we should use regularized Stokeslets for that. But if the forcing comes from a thin filament, for example, that can be modeled by a curve, for instance, in 3D, then maybe some other methods can be used, like regularized Stokeslet segments or slender body theory or Kirchhoff rod models that some of you use. Or if we have forces on the surface in 3D, then really no regularization needs to be used. So this is kind of the setting for what I'm going to talk about, and I'm gonna stick to 2D for the moment. So I'm going to discuss this kind of problem. So we have maybe a fluid either inside or outside some domain like this, and we're trying to evaluate the velocity at the point X due to boundary forces. Okay, so we have the Stokeslets integrated along the boundary, and this is what we're interested in computing. But it turns out that one can write the Stokeslets as single and double layer potentials for the Laplacian. So for example, if we integrate around the boundary, then we can do some integration by parts. The forcing can be separated into a normal and tangential component along the boundary, and so forth. And so we end up with these two things at the bottom, which is some density times the Green's function for the Laplacian, and then a second, a double layer potential. Okay, so because of that, I'm going to restrict my attention to these two integrals. And in about 5 slides, I'm going to argue that really the first one is the one that we want to compute, and the second one will follow. Okay, so I'm going to talk about computing this integral in 2D. This is a classical problem. Of course, there are solutions. There are expressions for the solution. But for example, here, this is an inside. We want to evaluate the solution at, say, the point X. And so typically what happens is that we classify the problem into maybe three different kinds. One kind is when the evaluation point is far from the boundary, then, for example, this function log of x minus y, there's sufficient distance between the points x and the boundary that really you can just use a trapezoid rule, for example, and things work out very well. If you're on the boundary, then you have something like a weakly singular integral that can be dealt with also in a certain way. So the harder problem is when you're near the boundary but not exactly on the boundary. And so this is the one. For example, if I just take this some problem like this and I use the trapezoid rule, I get errors that look like this. So for example, this is meant to be close to 0 in the middle, but as you get to the boundary, close to the boundary, the arrows start going. And that's because we're trying to evaluate these functions that are very spiky, and this is meant to be for a fixed discretization of the boundary. You just cannot get the accuracy. Why is that? Because as you evaluate at a point closer and closer to the boundary, the function gets, even though it's a smooth function, it gets spikier and spikier, and then with a fixed discretization, you just miss it completely at some point. Okay, is that okay? So that's part of the issue, and we're ambitious here, so we would like to evaluate these things with 16 digits of accuracy. Okay, so I'm going to concentrate on this, and I'm going to tell you the idea of what we're calling the circle method because of what it looks like, but I realized there's something else in math called the circle method in something else. So this is not related, but here's the idea. This is the general scenario. And so what happens is that as x gets close to a point on the boundary, so y of s will be the boundary point that is nearest the evaluation point. We are getting close to a singularity in the function. So what we're going to do is, the idea is to just add and subtract something, right? I spend my life adding zeros or multiplying by 1. So I'm going to add and subtract something, so I'm not going to take anything away. And what I'm going to add and subtract is going to be a problem that has the same singularity, let's say, on a circle. And so when I subtract that, I'm going to combine them in a way that is easy to compute, and then I'm going to have a problem on the circle. Well, the circle parameters still have to be determined. So there's a shift. There's two parameters. One is the radius of the circle, for example. You can do this for any radius if you think about it. And so what's the correct radius to choose? Okay. So here's the idea, right? I subtract. So we have now the ratio of logs because of the subtraction. And then I add it again. And so the idea is that the first integral of these two are going to be, that can be computed accurately with trapezoid rule, for example. And then we're left with the second integral, which is now on a circle. And so we need to just look at how to evaluate this on circles. Okay, so that's the simple idea. Now, things tend to work better, in my opinion. This is just an opinion. This is not a theorem. But best results, I think, happen when you remove a singularity rather than trying to match a near singularity. That's more difficult. So, but here we don't have a singularity, right? Things are nearly singular, but not singular. So what should we remove? Well, we remove the closest complex singularity. So the idea is that the distance formula is this dot product that we have here, capital F of theta, and that has no roots, no real roots. But if we allow the parameter that goes around the boundary to become complex, so that's a little weird, right? Because what does that mean? But just do it. And so what happens is that in the complex plane, now you have singularity. And you pick a singularity close to the y of s, and then you use that by choosing that singularity. Then you want both the original shape and the circle to have the same singularity at the same point. And so that determines the radius of the circle. So that's the methodology that we use to determine what the radius is. And that's the idea. So before moving on, I'm just going to write down the single and double layer potentials for the circle, because now we're concentrated on the circle, right? So for the circle, we have this notation, for instance. So I can just, this is going to become important, that z function, or z value is 1 minus. This is for an interior point. For the exterior point, z would be 1 plus a little bit, and that's outside. Rho is the radius of the circle. And I'm going to use some expansions in z, so I need z to be less than 1. So this is why there's a difference between the exterior problem and the interior problem. But otherwise, they're similar. And if I write the single and double layer potential, for the circle, I have these expressions. So these are going to become the two things that I want to compute. And then I told you that I was going to concentrate on the single layer, and that's because this double layer at the bottom here is really comes from a derivative of the single layer. So if you take the derivative of the single layer with respect to z, then you get the double layer. So if we know the single layer as a function of z, then we can differentiate it and find it. Okay, so it's a simple idea. Great. Okay. This is philosophically, this is the idea, the general idea. Right? We want to evaluate some density times a kernel. And if we can find basis functions called psi here that we can use to expand the density, and if the kernel or if the integral can be computed accurately for those basis functions, then we can write down the solution as a series. And so what I'm going to use is Chebyshev polynomials. Which I've come to love in this project. Why not? So here's some of the properties of Chebyshev polynomials that we're going to use. Coincidentally, not coincidentally, there's a generating function that looks exactly like what we need in terms of Chebyshev polynomials. And there's orthogonality properties, etc. And so the plan is to use Chebyshev polynomials to expand the density, and then use orthogonality conditions to evaluate the integrals. Okay, so here's in all its glory. There's G is the density, so we write it as an infinite series. Well, here's a truncated series. So this is why I have an approximation there in the second line, because I'm truncating this series. This is the one approximation we're making. And we have an expansion in terms of Chebyshevs. The kernel is in terms of Chebyshev. So if I exchange my summations and integrals, now my integrals are all based on the orthogonality condition. So these are now evaluated exactly. and we have an expression for the single layer. So what do I need? I need the coefficients in my expansion of the density, and they depend. Remember, S is the value of the parameter that goes to the point on the boundary that is closest to the evaluation point. So these coefficients A and of S depend on the evaluation point. So it sounds bad for the moment because it sounds like we have to recompute those for every evaluation point, but really they're just rotations of one case. And those can be computed with FFTs quickly. Okay, so here's the summary of the method. I've written it in terms of the inside and the outside. Okay, any comments so far? Let's see. I have no idea what time it is, but so I'll give you some examples now. This is so what am I solving? I'm solving Laplace's equation outside the unit disk with some Neumann boundary conditions. So the white circle is the unit disk. The shaded part is the error in the computed solution. If I just use the trapezoid rule, then you can see from the figure, you can see how the error is largest near the boundary. And as you get away from the boundary, then it becomes small with the trapezoid rule because that's accurate here. This is the error. If I just pick one point somewhere, I don't know which point I pick a point on the boundary and go along a line, I get this error as the distance to the boundary gets smaller. But the error in the circle method stays down here. Okay, if I do the internal problem, almost all the way in, I didn't quite compute it all the way in, something different happens, similar. The trapezoid rule also has a problem, although curiously, as you get closer and closer to the boundary, look, this is 10 to the minus 10 away from the boundary, so you're very close to it. The error is going down also for the trapezoid rule. I'm not sure we know how to explain this, but I'm interested in the circle method, which has errors down at the bottom. Notice that the way I explained the circle method is really not, I'm not doing quadrature, right? Because really the error comes from the expansion. The integrals are done exactly, which is why this works.
What's your F?
What's my F here in this example? I don't know. It's probably like some kind of, like a second derivative of a log function centered somewhere else.
You don't have to.
Okay. And here's, those were examples for a circle. And so now the example for the star-shaped domain that we have, okay, here I have the function that my boundary condition is a Neumann boundary condition. And we do what I explained. So we add and subtract the circle, and then we do the circle with the circle method. The other part we do with trapezoid rule, and we have these errors. Okay, so this deals pretty well with the near singularity issue, and I'll give you a couple of examples with fluid flow. So you recall that the Stokeslets, for example, can be written in terms of these single and double layer potentials. So we do that, and then it's a matter of evaluating both a single layer and a double layer. Okay. So the first example is something called a squirmer. This is a model of a swimming organism. For example, a typical example in 3D would be something like a volvox, if you're familiar with this. These are really round things with cilia all around it. And so the cilia move, and then that's how they propel themselves. And so mathematically, the way this is modeled is by having a sphere, or in 2D, a circle with a slip, a tangential velocity condition. So the idea is, I'll just show the result. The idea is that we have a velocity condition that is tangential here on the boundary, and then given that velocity, I have to solve for the forces on the boundary that produce that velocity. And once I have the forces on the boundary, then I can evaluate the flow outside the domain. Right? So there's an inversion going on here, because I have velocities on the boundary and I need the forces there. So I'm going to tell you in a second how I do the inversion, but for the moment, and there's the error on the whole domain. So again, this is, let's see, what else do I have? Another example, which I think is coming up, is, for example, suppose we have something like an organism with a circular head. Don't blink, because this is fast. That's it. So in this case, what I have is I have something that looks like a swimming organism. There are forces on the flagellum that are pushing fluid around. These forces are given by the method of regularized Stokeslets segments. And what they do is they produce a velocity field, which is the velocity field is going to deform the circle, right? So then I have to again find forces on the circle that, in this case, cancel the velocity. So this is not swimming. This is an organism that somebody's holding here in place, and then it's just flopping like this, and this is not moving. Okay. I can also do something similar for internal flows. So this is okay, that was fast. But this is just a simulation of a reduced model of an organism. So now we have an organism that's been reduced to a single dot with regularized forces. Actually, it comes from regularized force dipole and something else. So that propels itself, but this is inside a droplet, for example, or some kind of circular boundary where the velocity is zero. So again, the organism produces a velocity that would modify the boundary values. So we have to find forces on the boundary to cancel the velocity there. And then the motion is the sum of the superposition of both velocities. So I'm inverting something, and I haven't told you how I'm doing that. So we might be used to doing something like this. When we use regularized Stokeslets, we have an expression like this, right? And if we know the velocity on the surface, then this can be conceived as we can just put it all in one long vector, and it's a linear system for the forces. And we have to be careful a little bit here, because there's a null space, a non-trivial null space in this problem, right? Because if we take forces that are normal to the boundary, say of a circle, and constant magnitude normal to the boundary, then this doesn't move. It just increases the pressure inside. So there are non-trivial forces that produce zero velocity. So we have to be careful about that. But anyway, we can compute the forces this way. We're not doing that. Well, first of all, we don't have a regularized Stokeslets. We have a singular Stokeslets. So, but we have expansions, right? We have the Chebyshev expansion of the velocity, and we can have a Chebyshev expansion of the force. So why not go through, why not connect, instead of connecting the force and the velocity, why not connect the coefficients of the expansion of the force with the coefficients of the expansion of the velocity? And so we have the following result, that if we have such expansions, and these are the coefficients, then the coefficients are related in a certain way. And if you look at the bottom line for n equals 2 or greater, these are just proportional to each other. In other words, the matrix that connects those coefficients is diagonal. For the most part. There's a couple of them that are related by a 2x2 block. So there's 2x2 block ruined everything. Instead of being diagonal, there's two little blocks, but you can still write down the answer. So really, in the end, when you have the velocity on a circle, and you want the forces that produce that velocity, you go through the coefficients of this expansion, and there's nothing to invert. You just multiply them by some number each, and you're done. Okay. How am I doing in time? Couple of minutes. Well, I'm going to mention something in 3D, so in a sphere, but I'm going to tell you a little bit. This is not going to be the same method for now because I don't have all the details yet. So for now, let's just say that I'm going to use a method of images. So for example, if I have a bunch of random forces pushing the fluid around a spherical particle, then each one of these forces has image points inside the sphere, and the combination of all the forces and the images gives us zero velocity of the sphere. So this was something that we came up with. The method of images for spheres, of course, existed for a long time, but for the regularized Stokeslets, it didn't, and we had to work a little bit hard to get. And I'm showing you this because I just wanted to point out that there will be, I hope I got this right, Scott might be talking about some related problem to this. And of course, the forces don't have to be random. It could be from a flagellum or several flagella or something like that. And I show you this because these are forces that are in the fluid, and the fluid is exterior to the sphere here, right? And the images are inside the sphere. So I'm also interested in the other way around, when the fluid motion is produced inside the sphere and the images are outside. It turns out those two problems are not symmetric, and I haven't been able to get the images for an internal flow to the sphere. I don't know. I know that other people were working on this. Sarah's group was working on this, and I don't know what the status is. So it may be an open problem. It may not be if Sarah has done it. But we also have the one we have is only for a particular regularization. So if we were interested in changing the blob function to a different one, then we don't have. You do?
One done.
Oh, one is done. Okay.
Frank's turn. Yes.
Okay. Check. Sarah. He's Sarah. Great. Okay. And then, so this is my final slide, kind of. So mostly what I wanted to show you was the method, the circle method, because it's simple. I think the features are the simplicity, and you can see the accuracy that it gives you. We're working on a 3D version, so we purposely didn't want to use too much complex analysis because we wanted to try to extend it to 3D. And so that's part of one of my students, Alex, who's here somewhere. So if he knows more about this in 3D. And also this is an advertisement for Tom's talk tomorrow, who I think you're going to talk about some other methods that are addressing also the near singularity issue. Okay, so I'll leave it at that.
Are there
Question?
questions? Yeah.
Yes, Tom.
You mentioned M is not invertible, and then you showed how to break it down into the 2x2 pieces. Does the non-invertibility show up somewhere in that?
Yes, some of the reason there's those 2x2 blocks is because some of those coefficients are related to each other due to the non-invertibility. Yeah.
You when you were doing the circle method, you talked about you actually broke down the log function in terms of Chebyshev polynomials as well. Is that necessary? Can you just integrate the Chebyshev or Fourier times the log analytically? Do you need to use that second expansion?
Okay, the question is it necessary to expand the log, the kernel in terms of Chebyshev? It may not, I don't know if it's necessary, but we found it easier to look at it that way. So maybe it's not necessary, but it's the way we see it.
Can you comment on computational costs? I mean, you gain a lot in accuracy, obviously, round off error.
Yeah.
But like a standard, say, second order method, how much more expensive is it to get that?
Well, what you need to get is the coefficients,
yeah,
right? And that's done through an FFT. So I just need an FFT on the boundary. So it's a one in this 2D case that I showed you, it's a 1D FFT, and pretty much that's it. Yeah, Rudy.
So like very related question. It theoretically should work on like arbitrarily complicated geometries and 2D and later 3D.
I don't think it's going to work in arbitrarily complicated geometry. What we know how to do is what we call star-shaped domains, which are in polar coordinates. The radius is a function of theta. But if it curves in itself, we haven't thought about it yet. Yeah.
You showed a graph of the error using the circle method. So I'm wondering if that error is related to the radius of the circle or the location of the circle.
Yeah, the error is not related to the location of the circle. There are other you can put the center of the circle in other places, but the radius of the circle is definitely comes from the complex analysis part. So that's important to have. If you don't have the right radius, you don't see the flat 10 to the minus 15. Great, I'm done.